In this video, we're going to study about limits. We know that two broad areas of calculus, known as differential and integral calculus, they are built on the foundation of concept of limits. This is the reason we have to study about limits. In mathematics, the limit is a kind of concept that is used to analyze the behavior of function near a particular point input. For example, I will take a function fx equal to x squared. I have made a graph of it. Let's say we want to analyze the behavior of this function when x equal to 2. Okay, we can see graphically that when we take the value x equal to 2, and on checking that, the function is generating an output that is equal to 4. Either you come from right side or you come from left side. The output that we get is equal to 4. So this tells us what the function is doing as we approach x equal to 2, as we are approaching x. Okay. Now the question arises, why can't we directly evaluate the function at x equal to 2 and we will get the value of 4? The problem is not in this example or in this function, because this is a continuous function, so you can directly evaluate the value of a function at a particular point and you will get the output, or you can say limit. The problem arises when we have a different kind of functions that are not continuous. We know a continuous function is a function which, for example, which we can draw without lifting our pen. It's a continuous function. And discontinuous function are those functions which we draw with lifting our pencil or pen. This is a discontinuous function. The problem is not that with that of a continuous function, but with that of a discontinuous function. We cannot directly evaluate the value at a particular point. Instead of that, what we can do is we can analyze the behavior of a function that is very close to that of a particular point. For example, here you could evaluate the function at x equal to 2 directly, but in this continued function we cannot evaluate at 2, but instead of 2 we will take values that are closer to 2. For example, 1.999 or 2.001, but not at 2. Different type of discontinuity functions. We know we have a different discontinuity. I've given the example: removable discontinuity, jump discontinuity, and infinite discontinuity. So in this type of discontinuous functions, we cannot evaluate the limit. We cannot evaluate, or we cannot get the output for any particular point. Let's take an example of a function fx equal to x squared minus 4 divided by x minus 2. I have made a graph for this, and here you can see this is a hole. So this is a type of discontinuity function. It is not continuous. It's like this. Okay, there's a gap. This is a gap, so it's not continuous function. So let's suppose you want to find the behavior of this function at this point. So first we will do it from graph and table then we can do it algebraically. Notice that the reason we cannot evaluate the function at x equal to 2 is because when you put the values x equal to 2, we will get the output as 2 square minus 4 divided by 2 minus 2. We will get output as 0. So in this type of functions, when we get 0 by 0, we cannot tell exactly how the function is behaving at this point. We cannot tell anything about the output. So this is the reason we had to do something different. Rather than putting the values of x equal to 2, what we are going to do is we will take the values that are closer to that of a 2, and we can analyze how the function behaves, how we get the output for that function. We will consider this function again, x squared minus 4 divided by x minus 2. We can calculate the values of function for x that are nearer to 2. In the first table, first I will calculate it graphically. We know that function fx equal to x squared minus 2 divided by x minus 2. First, we can take values that are lesser than 2. For example, 1.9, 1.999, 1.9999, so like this. And we can check what is the output for this function. If we take x equal to 1.9, we will check how the function is behaving at that point. (1.9 minus 2). On simplifying it, it will be equal to 3.9. We can check for values that is x equal to 1.99. The output that we get is 3.99. Similarly, we can check for this. For example, we will check for fx when x equal to 1.9999. 3.9999. This is what we get for the values that are closer to 2. As we can observe that when we come much closer to that of a value equal to 2, we get a certain value that is approaching to that of a value equal to 4. This is what we call as limit. When we are approaching to a particular point, particular value, the output that we get, that is what is called limit of a function. In this table, we have taken the values that are lesser than 2. Now let's see what happens to the function. What happens to the output value? What happens to the output value that are greater than 2? We know the function fx is equal to x squared minus 4 divided by x minus 2. We'll take the values 2.1. And on simplifying it, it will be 4.1. We can simply do for 2.01, 2.001, and if we do it for 2.001, the value that we get is 4.0001. We can observe that as we are coming closer to that upper value equal to 2, coming closer either from left side that is lesser than 2, either from right side, we get a value that is almost approaching to that of a value equal to 4. Okay. Notice that as you move down from first column of the table, here, the x values get closer to 2, but they're always lesser than 2. For this, we use a notation as x approaches to 2, from x approaches to 2, we will use a negative sign. This means we are approaching from left side. And all the values to the left of 2 are lesser than. All the values are lesser than 2 when we use this sign. Similarly, we can approach to 2 from right side. And we will get the limit. We got the limit that is almost approaching to that of a value equal to 4. So this notation used for left hand side limit, this is used for right hand side limit. Or algebraically, if you want to find the limit of a function, what we can do is we have this. Remember, we cannot put the values equal to 2. The reason is when we are putting equal to 2, it will be getting 0 by 0 form, which is undefined. So for this, what if we factorize it? X squared minus 4 can be written as x squared minus 2 squared, or x minus 2 x plus 2. Okay, you can cancel x minus 2, you will get f of x equal to x plus 2. Now if you want to find limit as x approaches to 2, you'll have to put value of x equal to 2. We will get as 2 plus 2, that is equal to 4. Remember that we cannot put the value equal to 2 because it will get us 0 by 0, which is undefined. So we'll be talking about the limits in the next video, and we will follow solving different kind of questions on this. The reason we are doing the limit is basically we want to find the behavior of a function at a particular point. The problem not lies when the function is continuous. The problem lies when the function is discontinuous. Okay, at that time we will get the output equal to 0 by 0. Okay, if we simply look at the equation. But this is the reason you cannot take the value x equal to, for example, 2. You will have to take the values that are closer to 2, and you will analyze how the function is behaving on the values that are near to that of input. Hope to see you in next lecture. Thank you.